back. It's time for another demo. This one is a little different because we're doing less in terms of actual science and more about how we do science. You'll get it in a minute. So first we've got this. What is it? Well, if you watch the video I filmed just before this, which you won't see until after it, you would know. This is food coloring in water. I know, it's super exciting. But I'm using it because it works well. I think having a little bit of green in here makes it a little easier to see what I'm trying to show you. But we're gonna talk about measuring volume on things. And I'll tell you right up front that what we're gonna use is one of these, right? That is a graduated cylinder. This one can do an entire liter, 1,000 milliliters. I've also got this one and a few more, right? Like this one and that one and this tiny one. Why do we have 5? Well, because it depends on how much we want to measure. See, if I want to measure something that's like 830 milliliters, honestly, I'd use this one because I could get 830, it's right there. I could do it in one time. If I were to try and do this one, which only goes up to 10, I would have to fill this up 83 times. And any tiny little error, any tiny little remember, error is not a mistake in science. Error is how accurately we can measure something. But any kind of error multiplied 83 times is a lot of error. So you use this one. And then, well, this one's 250, and this one's 50, and this one's 25. They've each got their own use. Because you want to use the one that's the smallest that you can because it's the most accurate. Because the rule of thumb is when taking any measurement that's not digital, let me use one of these that you can actually see it, right? Let me zoom in. Wait, tell you, there's the camera. If I zoom in here and look, right? The difference between here and there is 10 milliliters, which means each one of these marks is 2 milliliters. The rule of thumb is that you can always go to half of the smallest marking. So if each one of these markings is 2 milliliters, then we can measure to the nearest milliliter. Anything else, we're kind of fudging it a little bit because we just don't have markings. We don't know, we're guessing. And we don't want to guess. So you can measure to half the smallest marking. That's the rule. So half the smallest marking for this one is 1 milliliter. But if I look at this one, put this up here, rotate it so you can actually see the numbers. There we go. Right, the difference between here and there is 1 milliliter. And each one of those marks is 0.1 milliliters. Half of that would be 0.05. So this one, my smallest one, can measure to the nearest 0.05 milliliters, whereas this one, which isn't even my largest one, can measure to the nearest milliliter. Accurate. Less accurate. Small. Much larger, a lot less time consuming. And if I'm measuring something that needs to be 200 milliliters, it doesn't really matter if I'm accurate to 0.05. It's mattered that I'm accurate to within 1 or 0.5. So it's all about what's acceptable. What's the acceptable amount of error? And it's usually a percent, right? 250, if I'm off by 1, I'm off by what? 0.4%? That's tiny. So I'm not really worried about it. But if I'm measuring 3 and I'm off by 0.5, let's see, 3 to 3.5 or 2.5 to 3, that's a lot, right? That's a big range. That's like what is it, 25%? Do the math. Nope, 16%. I can do math. So we're looking at, 0.4% or 16% if you're off by a half a milliliter. You don't want to be off by half a milliliter. If you're only measuring something up to 3, right here, right? And, an acceptable error might be 0.05, because that would be, 0.15%, 0.1666. Math in my head, it happens. But we're less than 1% if you're measuring 3. Trying to measure 3 milliliters on this one is impossible because the first marking is at 10. So you can't do it. It just doesn't happen. But, so that's why we have different ones. And it also gives you the rule of thumb for measurement. 1/2 of the smallest marking. Now, that is only part of the problem. Let me show you the other part. I know, food coloring, measuring device. And I gotta make sure there's no bubbles. All right. Now, can I do this without setting it down and have you actually be able to see it? And the answer is maybe. It's not really in focus. Let me rotate again. So you can see the numbers. And I want to ask you, what's that read? What is it? Is it 9? Two things. One, half of the smallest marking. You can get more accurate than 9. And the other part is, if you'll notice, there's kind of this band, right? There's the top of where you can kind of read and bottom. There's like a thickness there. And the reason is because of what we call a meniscus. No, not the thing that's in your knee that people tend to tear if you're athletic, but the same shape. It's a curve. And fluids, when you put them into something like this, they will form a curve at the top of the surface. These cylinders and these kind of measuring devices are calibrated so that the bottom of the curve is where you take the measurement, not where it touches the edge, which is why if you rotate it so that the things are right in the middle, wow, and I cannot get it to focus on the right spot. There we go. You can see it's not 9, it's at 8.9. In fact, it's maybe slightly less than 0.89. I would call it, 8.9. I would call it 8.85. Even though the top of the meniscus is at the 9, we read it from the bottom, and the bottom says it's 8.85. And that is a problem, because that's going to introduce experimental error. Because at some point, it becomes a little bit of a judgment call. Because I might read that as 8.85 and you might read it as 8.9. Does that matter? I don't know. It depends on how accurate we're trying to be. But what it does mean is that when we get to taking our measurements and we take our data, there's going to be some variability. What my group does for this lab and what your group gets for this lab might be off by just a little bit. And it's not that, my group did it right and you guys screwed it up, because that's not the way this works. It's that we have just slightly different, eye level of when we're taking that measurement. And you know what? That's okay. Because again, it comes down to what's an acceptable error? What's the acceptable amount of unknown? If we're talking the difference between 8.85 and 9, right? Or sorry, 8.85 and 8.9, that's a tiny, tiny fraction of the total volume. The error of 0.05 when we're talking about 8 or almost 9, That's a tiny, tiny thing. And so it matters, but it's okay. And this is experimental error. This is one of the things that we worry about. So as we get into this lab, and I'm going to give you guys some measurements and that kind of stuff, all of them were done using this method. Now I was gonna provide pictures and say, here, what do you see? And okay, that was taking a long time and I decided not to do that. I'm just gonna provide you the data, but keep this in mind. All of these measurements were done by me, so they should be consistent and it should work out. But if someone else were to take the same data using the same samples and the same tool, they might get something that's slightly different, and that's okay. Keep that in mind. Thank you. The power of science.